and Harish, and we're looking at this problem of forward secrecy for encryption. So forward secrecy, just to recap, is the property that the compromise of a party today should not affect negatively what happened in the past. And over the past couple of years, sort of forward secrecy generally moved toward sort of from this coarse-grained notion like key exchange, where you say once a session is done, you can delete everything and then it shouldn't affect anymore, towards a more fine-grained notion. And a prominent example that sort of also was the basis for the motivation for this work was secure messaging, where you think of a very long running session and you expect that compromises might happen at any time. And such notions usually involve some kind of an epoch. And what we realized is sort of that none of those notions really considers the fact that you might have turned off your phone for a very prolonged time. Maybe it's like your secondary phone or something. And then this device is like stuck in a very old epoch and might now want to catch up. And it seems that many of the forward secure primitive essentially then require the device to process all the message they missed when it was turned off or didn't receive message in sequence. And like, why is this bad? Well, think of secure messaging. You're probably more interested in receiving and being able to read the most recent message than something that was sent to you like a month ago. And also, for instance, if you look at the MLS group messaging standard, there, you being able to send a message actually requires you to have the latest key, because otherwise the other people would no longer be able to decrypt. So you probably don't want to have to decrypt everything in sequence just to be able to send a message. So in this paper, we consider this novel dimension of what we call fast forwarding. That's just you being able to jump to sort of the latest state in sublinear time. And we consider it for two settings. First, in the symmetric encryption setting, where we look at actually a PRG from which you then somehow can build a forward secure streaming cipher trivially. And second, a bit more interesting, in the asymmetric setting, where we look at what we call updatable public encryption. And I will introduce the primitive later. Okay, so first, let's briefly look at the symmetric setting. And there we sort of started by realizing that even though nobody ever formalized this property of fast forwarding, there's a folklore construction. More concretely, if you take the GGM PRF construction and you adapt sort of the templates people came up to get forward secure signature schemes to it, then you get a forward secure PRG that allows you to fast forward. So take the GGM tree and you say that the epoch keys are actually the leaf keys. And then in epoch 1, you would store like the blue seeds here. In epoch 2, you would store those. In epoch 3, so on. So all of the future keys at any point you will be able to derive in logarithmic many PRG derivations, but at the same time you get forward secrecy. So, but one thing we can observe is that this requires logarithmic local storage and logarithmic computation, even if you sort of iterate through the epochs sequentially. And sort of wearing a theoretician's hat, we think, okay, can we do better? And while we don't have like a clear answer to that, what we do is we consider an alternative model where we assume that there's some kind of public bulletin board where you can store and retrieve values, and then it seems we can do better. Now, obviously, this introduces like a communication overhead, and for many applications, you probably would rather do logarithmic many local computation than even one round of communication. But there are applications where you anyway need to do a lot of communication, so maybe that's not that bad there. Okay, so what do? We construct a forward-secure PRG that has constant local storage, constant sequential updates, and logarithmic fast forwarding, both in terms of communication and computation. And what we do is essentially we amortize the GTM construction by storing encryptions on this bulletin board. So each of the arrows here sort of is an encryption. So you would take like the key here and you would encrypt it under the key here and store that encryption on the bulletin board. And then locally you would just store like the blue seeds. Using the bulletin board, you can retrieve the green ones, and that still gives you logarithmic fast forwarding for all the future epochs. So for epoch 2, the situation would look something like this. And without going too much into the detail, you can see that we actually store like 2 elements locally. One of them is like the current element, and the other one is what we call the frontier, which is sort of the place where you will do the next expansions for, because due to the amortization process, you sort of expand a bit faster than you need. More concretely, you do like 2 expansion steps for every epoch change. So this starts to run ahead and ahead. And so storing this one additional local node allows you to nevertheless do everything efficient. Okay, so much about the symmetric case. I mean, if you want to look at the details, feel free to look at the paper on ePrint. It was slightly tricky to get like the details correct, but I think overall the idea is sort of quite simple. You just amortize this GTM construction by storing encryptions online on this bulletin board. So with that out of the way, let's look at the asymmetric setting, which was actually sort of the motivation for this work to begin with. And there we realized that essentially the only known forward-secure public key encryption actually is sort of this generic construction from hierarchical identity-based encryption, or HIPE. And this sort of really mirrors what the GTM construction does anyway. So are we done? Well, not exactly. On the one hand, if we talk to more of the practical people that are maybe not here at TCC, they will tell you that even though there has been like a lot of great progress in making HIPE more and more efficient, it's still sort of less efficient than what they would like. Moreover, this amortization process with the bulletin board doesn't work as nicely in this setting as it did in the symmetric, because now the people decrypting can sort of not help the people encrypting cannot help the decrypting party to maintain the bulletin board, because only the decrypting party obviously know the secret keys. So if the encrypting party runs way ahead of the decrypting one is stuck, then we don't get as nice properties as in the symmetric case. So we thought, okay, what can we do? Well, we can simply look at another primitive, and the primitive we look at is this updatable public key encryption, or UPKE, which we introduced. So this is me, Maurer, and Mularcic introduced that in the context of secure messaging a couple of years ago. And this primitive, on the one hand, is sort of like regular public key encryption, and on the other hand, it comes with like an explicit updating mechanism where you can generate an update and apply it to the public key and the secret key. The upside of that primitive is that, at least in the ROM, you can get it essentially as efficient as public key encryption. The downside is that it doesn't, that on the one hand, it requires some synchronization. On the other hand, you don't get any fast forwarding at all. So all the known construction that are efficient, sort of, you need now really this sequential processing of all the updates you missed. Okay, so in this paper, what we do is we give a generic construction of a UPKE scheme with fast forwarding from a very much related primitive, which we call Update-Homomorphic UPKE. Update-Homomorphic UPKE essentially augments this primitive with one more algorithm, which is an update combine algorithm. And the intuitive property you want is that whether you apply to updates individually or you first combine them and then apply the combined update gives you the same thing. And we can observe that actually there already exists schemes that satisfy this notion, which are the standard model UPKE scheme recently introduced by Dodis, Kartikeyan, and Wicks. So we can just use those. Given this primitive, we can then build fast forwardable UPKE sort of with the idea of just storing what we call cumulative updates on the bulletin board. So in each step, the sending party would store an update, and then once in a while, they would also fetch all the updates and sort of aggregate them such that the decrypting party can then apply them like in one step. And the remaining question is sort of which of those updates to generate, and this we phrase as a graph theoretic problem and propose a very nice graph that has some nice properties, because what we observe is sort of what we need is a graph with low diameter, because that is directly relates to the efficiency of the updating. Then we want what we call a low cut, so there just shouldn't be like too many updates in flight parallelly. And finally, we want low in degrees for other efficiency reasons. With that, because I'm running out of time, let me tell you about the open problems, because the real problem is really that we don't have anything efficient. So we need this Update-Homomorphic UPKE. And right now, the best we know sort of has like an overhead that's essentially linear in the security parameter. So whereas normal UPKE is essentially as efficient as public key encryption, we now have to pay this price. And it would really be amazing if any of you can come up with something that's more efficient, maybe using this generic construction we use, or maybe just do something completely else. Okay. Yeah. So thank you for your attention. So we have two constructions. So essentially, it relates to the assumption under which one can build this Update-Homomorphic UPKE. And there exists currently like two constructions. One is based on DDH and one is based on LWE. Yeah, so we need some kind of linear homomorphism. The biggest caveat is sort of that we need linear homomorphism for message that roughly correspond to like secret keys, whereas most efficient homomorphic public key encryption scheme give you a message space that corresponds to the public key space, essentially. So that's why we have this overhead linear in the security parameter, because we end up essentially sending updates bit by bit.
Our next talk is Rate 1 Incompressible Encryption from Standard Assumptions. And Jasko is giving the talk.
Yes, thank you very much.
We don't have sound on Zoom.
Hello? Okay, I'm louder now. Okay, again, we have this scenario where Alice has this huge database, let's say 500 terabytes, and she wants to send it to Bob. So as cryptographers do, she encrypts the database and sends it to Bob. Now, usually we model an adversary that gets access to the public key and to the ciphertext. But now Bob is very prone to losing his keys, and the adversaries might pick up his secret key at some point. So this is kind of an exploration of what we can still guarantee if the adversary at some point gets access to the secret key. Okay, so here the adversary also gets access to the secret key, and this obviously cannot happen unconditionally, because then the adversary can just decrypt. So let's get into what incompressible encryption is. This is the indistinguishability against an eavesdropper experiment. Most of you are familiar with it, but it works this way. The adversary chooses two messages, M0 and M1, and then one of the two is randomly encrypted, and the adversary gets back the ciphertext, and then the adversary has to guess which of the two messages were encrypted. This is a very standard notion, and we extend this where instead of the adversary outputting a guess, it outputs a state which is shorter than this ciphertext. And the state is forwarded to a second stage adversary, and this second stage adversary gets access to this to the secret key. So now there is a way that we can actually guarantee something, because this C might be much bigger than the ciphertext. So maybe we can guarantee that this adversary cannot guess which ciphertext was encrypted, even though it has access to the key. Okay, to get you familiar with the notion, I'll first show you what doesn't work. And it is just XORing your message with a PRG, with putting your key into a PRG, and then XORing it with the message. Okay, and here I'm gonna have things big that are supposed to be big, and small that are small. So this is going to be a continuous thing, not in the mathematical sense. Okay, so this doesn't work. What happens? The adversary can just choose all zeros message, all ones message, gets back the ciphertext, and then it just takes the 0th bit of the ciphertext, forwards this to the second stage adversary, and now the second stage adversary can expand the PRG and just look at the 0th bit of the PRG and the 0th bit of the ciphertext, and can just know which of the two messages it was. So this is not incompressible. So the problem here is that a single bit of the ciphertext only relies on a single bit of the ciphertext. So in an attempt to tie the entire ciphertext together, we do basically the same construction, but instead, again, we choose a, okay, now we put a random seed into the PRG and XOR this with the message. And now we get this C1. This means we get 2 parts of the ciphertext now has 2 parts. And now we throw a strong randomness extractor on this in the hope that this is our attempt to tie everything together. And the randomness of the randomness extractor, so the uniform randomness of the randomness extractor is the key now. And now we use this to mask the seed, which is used to produce this pseudo-random string. And then we also, and then the second part of our ciphertext is this C2. So now we have 2 parts, and we can decrypt by extracting, throwing the randomness extract on this, and then removing this mask. We get S, expand the PRG, and we retrieve M. But now if we try to prove this security, what happens? Or let's assume, let's start here. Assume this is perfectly hidden, then this PRG is pseudo-random. Now this thing is pseudo-random, and from this we can prove that this is perfectly hidden. But now we have a cycle, and we have nowhere to get into the cycle. And in fact, for certain choices of extractor and PRG, this is broken. So again, doesn't work, sadly. So now we have to use another notion that was that's called entropic encoding. This is from other work, and what does it do? It encodes a message M into a code word, and uses a CRS. Not very big, but I hope you can see this. And it can again be decoded using the CRS. Now it has some properties. You can simulate this encoding by just putting in a message in, and this will output an encoding and a CRS. And they are indistinguishable from things that are output honestly. So this still doesn't really have any properties. But the big deal is that C prime has, so here the simulated C code word has big entropy conditioned on the simulated CRS. And this basically means that for any M, this C has pseudo entropy. Even seeing this CRS. So you might be able to guess where this is going, but hard to see here because of the sun, but previous work does this in the plane model from LWE or DCR. And we focus on the plane model here. So, okay. Now let's use this. We do pretty much the same thing, but this time we encode this XORed message and get again C1. We extract from C1, and we actually do need this thing to get the another random string to get this proof through, but I mean, you can safely ignore this for the talk, and mask this seed. And yeah, this is the same seed as used in the PRG. And decryption also works pretty much the same thing, same way. We extract, remove the mask, decode, remove this pseudo-random string, get the message. And now I'm going to sketch, super sketch the proof. It's okay. C has pseudo entropy thanks to entropic encodings. Thanks to the pseudo entropy, S is hidden, and now S is since S is hidden, this G of S is pseudo random, and the message is hidden. So this is our symmetric key construction, and this is only in a kind of indistinguishability against an eavesdropper kind of way. Not so this is basically one-time use. So yeah, this is kind of the formal statement. And so for a message of length n, sorry, we get a ciphertext of length n plus some poly blow-up. And the keys are also pretty huge. This comes from the size of the CIS of the entropic encoding. And also, sadly, this cannot really be improved in the, I believe, cannot be improved in the plain model because there's a black box impossibility. But my favorite open question for this kind of work is, why do we need public key assumptions to build something that is kind of seems like indistinguishability against an eavesdropper? Because like if we leave away this incompressibility, then this is done just one-time pad. We don't need any assumptions. But suddenly we need LWE and DCR to do this symmetric key thing. This seems not necessary, but I haven't found any other way to prove it. Okay, then I can't get into this too much right now, but we extend this to the public key setting using some version of hash-proof systems. Yeah, and this, I mean, this automatically this also extends to CCA security. So here we have our next theorem. We have more constructions, but these have the best parameters. If we use the hash-proof system from DDH, we get the best parameters, but they are still very bad. So here we have the public key is bad. This, I mean, every parameter here is not really good. So my next open question is it possible to achieve best possible parameters without assuming I/O? This is a caveat because this has already been done in previous work. So using I/O, you can get way better parameters here. Yeah, okay. To summarize, I showed you how we turn entropic encodings into incompressible symmetric key encryption. In our ePrint version of the paper, and so in the TCC version of the paper, you can also find how we extend this to incompressible CCA public key encryption, and how we use DDH to make these kinds of. Oh yeah, okay. We need. Oh, sorry, I should have turned these around. We in the TCC version of the paper, we have DDH and turn this into programmable hash-proof systems, and then use those to produce a CCA public key encryption scheme. And in the ePrint version, we also have constructions from LWE and group actions, and also I think a very nice uninstantiability result of the random oracle model, which sadly we didn't get ready for the TCC deadline, so it's only in the ePrint version. Okay.
We're a bit short in time. Okay, maybe I get a quick question. Yeah, please. And maybe the next speaker can start setting up at the same time.
Okay, this is something I have to ask. So what is a programmable hash-proof system? I worked on both programmability and hash-proof systems. What is it? In one sentence.
It's something we made up, but it basically means that it basically means that you after seeing a bad input into the hash function, you can afterwards choose what the output of the secret key of the decapsulation would be. I don't have a good way to describe it. I'm sorry.
You can take it offline.
Yes, thanks. No, turn it off first.
Hey, our next speaker is Shai? Is Shai Halabi, and he will tell us about achievable CCA2 relaxation for homomorphic encryption.
Yeah, so sadly I'm not Adi. She was supposed to give the talk, but her flight got canceled, so she's still in Israel. So I'll talk about achievable CCA2 relaxation for homomorphic encryption, and that's joint work with Adia Kaviak, Red Gentry, and Margarita Wald. So we're talking about homomorphic encryption, and perhaps the most obvious application of homomorphic encryption is to outsource computation. We have a client, they want to compute something, they don't want to compute it themselves, they'll encrypt it, ship it to a server, the server will compute it for them, send back the result, they can decrypt. But if the computation is deep, if it's a long computation, then the server needs to work hard. In particular, the thing that makes it hard is it needs to do refreshing or bootstrapping in the middle, and that's an expensive operation. So what if the client can stick around and just do this little refreshing every so often? That might make the thing a lot faster. So it could be an idea. Just, the server will ever so often send the ciphertext back to the client. The client will decrypt, re-encrypt, send back to the server. So that could be a useful thing to do. The question is that safe? Is this secure? So on one hand, it seems that what would the server do? I mean, the server only sees ciphertext in this game. It's not a CCA type of a thing because it never sees plaintext. So maybe that is safe. But it turns out that not really. So we have two types of result. The first result just say that this is not safe. CPA security does not guarantee privacy if the server is malicious, even if you only show it ciphertext in this game where the client can every so often decrypt something and then re-encrypt it. So we define a new notion we call func CPA that lies somewhere between CPA and chosen ciphertext security, and show that it's sufficient for privacy in this context that we have a name for it in the paper that currently escapes me. I think like a client outsourcing protocol or whatever. And it's safe in this context. And it's also achievable from circuit privacy and other things as well. So let me start by, the second part of the result is, can we prove existing homomorphic encryption are already that? And it turns out that yes, for leveled encryption, homomorphic encryption, contemporary things, you can show that they're already func CPA secure. And leveled just means that whenever you want to refresh something, you get an encryption of it, but under the next key. So there's the depth of your computation is 7, you have 7 different keys, and every time you refresh it and get the next key. If you are not in this level thing, then we don't know how to prove it. Essentially, if we were able to prove it, then that would already show that these schemes are secure, even in the context of having circular security. So we don't expect to be able to show it from things like LWE or any of those, because we don't know how to prove circular security for these homomorphic encryption. I'll talk a little bit about it maybe at the end. So let's start with the attack. It's a very simple version of it. So again, the question is why you would think ciphertext help the server attack anything? And the answer is, well, the server can send invalid ciphertext. So let's start from a CPA secure scheme and just modify it so that encryption normally works just like encryption of the underlying scheme, except you concatenate 1 to the ciphertext to denote that this is a good ciphertext. Except in the case where you want to encrypt the secret key itself, in which case you just send it in the clear. Well, of course, that doesn't hurt the CPA security because the adversary never can do that anyways. And on the other hand, you modify decryption so that if it gets anything that starts with a 0, then it decrypts it to the secret key. So, well, you can see what happens. A malicious server just sends some ciphertext that begins with a 0. The decryption algorithm will decrypt it to the secret key, and then the encryption algorithm will send the secret key in the clear. That breaks the scheme. So, It's not always that CPA secure implies security in this context. Let's talk about what is it that you need. Well, it seems sort of obvious. What you need is for the thing to remain secure, even if you have a refresh, even if you have an oracle that refresh ciphertexts for you. So you have a new game where it's exactly the same, except you have this refresh oracle. A little more generally than that, you can refresh it, not just decrypt and then re-encrypt. You can have an oracle that does decrypt, apply any function of your choice, and then re-encrypt. This function of your choice doesn't matter all that much in this context because we're talking about homomorphic encryption. You could have computed it yourself, really, most times. And then you show that in this thing, if you have a scheme that remains secure when you have that oracle, well, then it's secure also in the context of this client-based protocols, even if the server is malicious. Just a pictorial picture of the definition. So this is the normal CPA security game. You have a challenger, it produces keys, it gives the adversary the public key, the adversary sends two messages, one of them gets encrypted, the adversary needs to change to figure out which one. And the CPA just adds to it this refresh cycles where the adversary can send a ciphertext and get it refreshed. And you still require the same thing, that the adversary cannot guess which of the two messages were encrypted. If you want to talk about the leveled version is the same thing, except whenever you refresh, you get an encryption under the next level, and the adversary is free to choose the level in any way it wants. I mean, for the challenge cycle. Next, we ask, do existing schemes have this property? So every level scheme has that property. As long as the keys for the different levels are chosen independently, then every scheme that is CPA secure will also be func CPA secure. And in particular, all the level schemes that you see in the literature, it's always, I mean, leveled is always done with independent keys. So, and the idea in why that is, well, you know, these are new keys. I mean, what can you do? You simulate the answer to the func oracle by just encrypting random messages. You don't need to encrypt anything else. These are just ciphertext. This intuition of server only see just ciphertext works perfectly well here because you never get to encrypt something under itself, or you never get to refresh something with the same key. The other thing is if the scheme is circuit private, then it func CPA secure. So circuit private schemes mean when you get an evaluated ciphertext, or when you get a fresh encryption of the function applied to that, these look indistinguishable, even given the secret key, actually. It's not, well, here I think we just write statistically close, but I think indistinguishable given the secret key should be enough. The one thing that's a little different in this notion is, in this case, what we need, it's still okay that the keys are produced honestly, but the ciphertexts are generated by a malicious server. Whereas usually when you talk about circuit privacy, you talk about either they're both honest or they're both malicious. So in this case, the thing that we need, and that's actually the easy case. I mean, it's harder to deal with malicious public keys than it is to deal with malicious ciphertext. And then the theorem is that if the scheme is CPA secure and circuit private, then it's also func CPA secure. And the way to do that essentially is well, it's homomorphic encryption. You use the evaluation in order to do the thing. And because it's circuit private, then you cannot tell that it was evaluated. You can might have been just as well been answered by an oracle that decrypt and re-encrypt. And then, well, if you wanted your scheme to be circuit private, what would you do? Well, you can use sanitization. And you can do it, I mean, these are typically done with bootstrapping techniques, but Essentially, the idea is you sanitize the output so that it looks like a random encryption. This is a little bit off because if the original ciphertext that you got as an input to this thing was already not valid, or if you want to think about it in the terms of contemporary, it would already very noisy, then maybe you evaluate it and then who knows what happens. So you also need to sanitize it before you start the homomorphic evaluation. But other than that, it's fine. So to conclude, we propose this new notion of func-CPA security and show that it's related to circular security. It's not, we actually don't know to show that they're equivalent. What we know is that for schemes that have some property that is sort of shared by all the current schemes, which is you can, well, maybe I'll talk about it in a minute. Let me finish the slide and then I'll go back to it. For schemes that have some property, if they are func-CPA secure, then they also are circular. And it's the notion of func-CPA security is achievable either via generic transformation to circuit privacy or by leveled schemes, any level scheme. And this notion is sufficient for privacy in client-aided protocol. Yeah, I knew there was a name for it. Against malicious servers. So, you know, if you have just a CPA secure encryption, then you need the client to be semi-honest. Whereas if the scheme is leveled or it's func-CPA, then you can have the server being malicious, and as long as it only sees ciphertext, you'd be fine. One thing that we don't know how to do is if you look at contemporary schemes like that, with the added thing that you need to do bootstrapping, we would like to say that they func-CPA secure, but we don't know how to prove it. And I wanted to say something about what the scheme needs to have in order for this connection to circular security. Essentially, in all of these schemes, if you just see the public key, you can generate a ciphertext such that if you decrypt that ciphertext, you will be able to figure out from the decryption of it what the secret key is. Essentially, given the public key, you can generate an encryption of some sort of the secret key. It's just not the sort that you need to do bootstrapping. If a scheme has this property and is func-CPA secure, then you can generate something that's really bootstrappable. And since we don't know how to do things that are bootstrappable for normal assumptions without explicitly assuming circular security, that it means that it's hard for these schemes to prove that they are func-CPA secure. That's it.
One quick question, Yevgeny?
So maybe I missed the homomorphic aspect, but at least for the basic definition, but the only query is like ciphertext and you decrypt and re-encrypt exactly the same thing. Are you saying even for this, you don't have equivalence with public key encryption or something like, or result given any public key encryption, I can build another encryption which is secure with respect to this re-encryption queries? Or maybe it's not interesting for applications.
I didn't think about that without the evaluation. If you have sanitization, then sure you can do it. Without sanitization, I didn't think about it, and I don't see off the top of my head how to do that.
I mean, maybe there are no applications, just kind of ignored the homomorphic aspect, but.
Okay, so let's keep the questions offline and let's thank all the speakers in this session again for their wonderful thoughts.